Okay, I will start. Hello, how are you? How are you doing? It's me, the pioneers in methods, Mourad Sultan Ezouidi, with you. In this lecture, my colleagues will see how to solve 14th degree, okay? Hello, hello. I'll check if it works or not. First, I'll fix, uh, I'll fix my mic to see if this works or not, okay? Then we start. Wait for the Canadian researcher to explain and to give things. Okay, it works here. It works. Yes, okay. So, hello, how are you? How are you doing? It's me, the pioneers in methods, Mourad Sultan Ezouidi. Today, we are going to explore a method that completely defines how we solve high-degree polynomials. Ezouidi theorem. This method allows us to derive exact symbolic solutions for polynomials that traditionally pose significant challenges. Today, and today we will be solving a 14-degree polynomial equation by extending its power. Means in fact it is a 13-degree polynomial equation, and we extend this polynomial to the power 14 to the power 13, and we will now solve 14th degree polynomial equation, and then go to recursive formula that relates, let's say, the 14 degree to 13 degree. So today we will demonstrate how the theorem works, and we will compare it with classical numerical methods to highlight the power of this approach. I will share the screen with you first. Okay, I will try to share the screen with you first, and then we start. Also, a new system will be shared. We thought that today we solve a 13-degree polynomial equation by extension, meaning that we are going to extend these 13-degree polynomial equation, and at the end you are going to see the simple roots of this 13-degree polynomial equation, of course by solving 14 degree. Okay, so here you can see the room to the power 14. We call that okay, to the power 14. Let's say 4. Okay, so L0 for the Q in fact is going to be 14, L1 is 91, L2 is 364, and 3 is going to be equal uh, to 1001. Okay, and L4 is going to be equal to 2002, and L5 is 3003, L6 is going to be 0, and L7 is going to be 21,021, and L8 is going to be, okay, yeah, L8 is going to be equal to negative 192,119, and 9 is going to be equal to 119,756 up to L13, which is 2. So therefore, let's now begin by examining the polynomial equation we are working with. Here is our 14-degree polynomial equation. X is to the power 14 plus negative 14 x is to the power 3 plus 91 x is to the power 12 minus 364 x is to the power 11 plus 1001 x is to the power 10 minus 202 x is to the power 9 plus 3003 x is to the power 8 minus 0 times x raised to the power 7. I have 0 here to let you see the 8th coefficient of this 14-degree polynomial equation. Minus 21,021 x raised to the power 6 plus 70,000, 70x to the power 5 minus 1,000, 119,000, 119x to the power 4 plus 119,756x cubed minus 71,981x squared plus 24,010 times x minus 0. You see this one in fact is 13 degree from the equation but we extend the power. Means in this example we will solve the 13 degree from the equation and at the same time we are going to solve the 14 degree from the equation. Here now, let me show you how Zwitter theorem solves this problem exactly. We begin with we begin by expressing this problem as p of x equal x to the power 4 minus L0 of ODQ x to the power 15 plus L1 of ODQ x to the power 12 minus L2 of ODQ x to the power 11 plus L3 of ODQ x to the power 10 minus L4 of ODQ x to the power 9 plus L5 of ODQ x to the power 8 minus L6 of ODQ x to the power 7 plus L7 of ODQ x to the power 6 minus L8 of ODQ x to the power 5 plus L9 of ODQ x to the power 4 minus L10 of ODQ x cubed plus L11 of ODQ x squared minus L12 of ODQ times x plus L13 of ODQ. This is, in fact, is our 14 degree from equation by extending the 13 degree from equation, and here we use the approach Mourad Sultan recursive formula or theorem of Mourad Sultan Ezouidi that will help you to find the 13 the 13 coefficient of this new 14 degree from equation corresponds to the original 14 degree from equation. Okay, here we told that in fact we extend this, it's a 14, it comes from a 13 degree from the equation. Okay, so here my colleagues will solve these 14 degree from the equation. Okay, so we'll go step by step and we'll see the method how to solve this 14 degree polynomial equation. Okay, let's start. We told that this is our polynomial to the power 14. Here, my professors, you can see here is the polynomial we are solving today. As you can see, it's a 14 degree equation. Traditional method would rely on numerical approximation, but we are going to approach it systematically using my theorem. First, let me point out something key here. I will just, okay. So, this explanation should provide a solid understanding of the challenges classical method faced when solving IDE from the equation and how the theorem offers a promising alternative. Okay, so my method, my professors and colleagues and students based on Mourad Sultan Ezouidi theorem excludes all the classical methods, including Abel's theorem, which states that certain polynomials can be solved uh, using gravity. Contrary to Abel's assertion, my method demonstrates that even polynomials with radical roots can be solved exactly. Where traditional approaches fail, my theorem reveals the exact same truths through structured process that bypass the limitation of classical algebra and numerical methods. This is not just a numerical approximation. It provides precise, solvable routes for problems that would otherwise be deemed unsolvable. So here you can see that is in fact 14 degree from the equation. We will try to find the 15th coefficient of this new 14 degree from the equation, and after that we go back to the cursive relationship or formula that relate the 14 degree to 15 degree, and then we are going to give you exact sample points. Here, traditional method for solving polynomial often involve numerical approximations, which can be quite irritating, especially when we are dealing with high degree polynomials like this one, 14 degree from the equation. Numerical methods such as Newton method gives us approximations of the roots, but these come with the risk of rounding errors and can guarantee exact values. But here let's say, is with the Zwidy theorem, we approach the solution differently. This theorem allows us to break down the polynomial and solve for the roots symbolically. It involves a recursive process that systematically finds the exact values of the roots, avoiding any of the errors that arise from approximations. Here you can see professors and colleagues. This is the theorem of Mourad Sultan Ezouidi that is written as S subscript k minus 1 of the R equal the sum from 0 to k combination n minus r choose k minus r n raised to the power r between parentheses and 0 of order q all raised to the power k minus r and r minus 1 for q. This recursive formula will give you exactly the values of these the values of the 15th coefficient of this new 14th degree from the equation relative to the original 14th degree from the equation that in fact was extended from 13 degree from the equation. Here the concept, the key today, the let's say the conclusion. Here we will see how we solve an n minus 1 or let's say an n minus 1 degree from the equation to by extending the power to get an n degree from the equation. It's a big relationship. Okay, and this is it's a process to solve this kind of n degree from the equation that in fact bypasses the limitation of Abel or Abel's limitation or Abel's assertion and also Abel's theory. Here, let's me first explain how the formula works. Here is the formula, okay, that we will use to compute the roots. Let's break it down. So, teachers and colleagues, learners, and those who have smart mind who wants to learn from you, to learn from you, and to know the big relationship between ambiguity equation and the new ambiguity equation, okay, and the relation between the roots of this original ambiguity equation and the axes of this new ambiguity equation. Okay, so here we can see the combination n minus r to k minus r. These are binomial coefficients that adjust the terms. And here you see n raised to the power r. This term arises the degree of the polynomial. And negative and 0 of ODQ raised to the power k minus r. This involves the base coefficient and 0 of ODQ adjusted by the power k minus r. And you see the r minus 1 denotes or represents the coefficient of my 14th degree from the equation after making the extension from 13 degree from the equation. So this refers to the area terms in the polynomial as we proceed through the recursion. Now, my professors, let me show you how the theorem solves this polynomial exactly. We begin by expressing the polynomial as p of x equal x to the power 14 minus L0 of order 2 raised to the power 13 minus L2 of order 2x raised to the power 11 plus L3 of order 2x raised to the power 10 minus L4 of order 2x raised to the power 9 plus L5 of order 2x raised to the power 8 minus L6 for the q x raised to the power 7 plus L7 for the q x raised to the power 6 minus L8 for the q x raised to the power 5 plus L9 for the q x raised to the power 4 minus L10 for the q x raised to the power 3 plus L11 for the q x squared minus L12 times x plus 14 equals 0. So here you will see exactly how 14th degree from the equation can be collapsed by using Mourad Sultan Ezouidi approach or using Mourad Sultan Ezouidi theorem or using Mourad Sultan Ezouidi recursive formula. Here is the concept. Here is the key. Here the door is open when Abel closes before. Now we as Mourad Sultan Ezouidi we open this door and we forget about uh, the theorem that for a degree higher than 5 we can resolve it. We can find radical roots and or we can express it in radical. But here in this example, we really express it or derive it roots with radicals. Okay, and which is contrary to Abel theorem. Okay, here the Professor Mourad Sultan Ezouidi can apply the recursive relationships and symbolic transformations to derive the exact roots. Here is the step-by-step process. First of all, we explain the equation in terms of sk minus 1 of the cube. Sk minus 1 of the cube will give you the new 14-degree from the equation, which is a set of symbolic coefficients that we can recursively calculate it. These coefficients are based on the coefficients of the original 14-degree from the equation. As we proceed, we calculate each sk minus 1 of 42 where k belongs from 0 to 13, 14 minus 1 is 13, which directly relates the roots to the roots of the polynomial. The key here is that every coefficient sends a message. The key here is that every coefficient uh, mm, give you a pathway, give you a road where you should where you should uh, where you should, let's say, find this recursive relationship. So here we can say also each coefficient is determined symbolically without any numerical approximation. For this formula, for example, here, okay, for this example, okay, after calculating this, we found that we found that S0 is equal to 0, S1 is equal to 0, S2 is equal to 0, S3, S4, S7, S5, okay, and S9 and 10 and 11, and S12 and S13, okay. Mhm. So here we will see that, as of course, we'll see that S13 has to be equal to now. What will be negative 91? Yes, I will just write it here. This is 0. Okay, like this. This is a 0. S12 is 0. S11 is going to be negative 91. Negative 91. Okay. Negative 91. I'll make this exactly. Okay. So, erase this. Erase to the power 12. Erase to the power 12. 12 is Mourad. Okay. Negative negative 91 times 14 raised to the power 12. So this is the value of this one. Okay, let's check the value of this one in my professors. Then I will just come to you and go down because I calculated this before starting my live stream with presentation. Okay, this is one. I'll go step by step. Okay. Mhm. Okay. So okay. We call S 11 here. S 11. This is S 6. Okay, S 6 is going to be negative 3 times 450 times. Okay, correct. And let's check S 11. This is S 7, you see. But just now see S 7. 7 is going to be 0, S 9, S 10, S 11, which 1K equal 12 we will obtain as 11, so just 30 seconds to show what I can as well. You see, Microsoft is not a good tool. Okay, here in this example, you will see that how we derive exact sum equals. So this is k equal 10, so we'll obtain as 9. Yes, this is as 9. This 9 is going to be equal to a now. Okay. Here, my colleagues will can use our solve. We solve our theorem, our approach, solve this, and we get from the equation. Our theorem does not approximate, does not give you approximated or estimated rates. It gives you exact symbols. Okay, so now let's see when k equal 11. Yes, this is k equal 11. I will obtain as 10. As 10 is going to be equal to now. We proceed with S11. Yes, this is S11 now. S11 is going to be S11 is going to be equal, yes. Take all this image here. S11 is going to be equal to 1. So it's going to be equal to 0. Then I comes here now. I comes here. S11 we told is going to be equal to, and now let's see first, okay, S11 is okay. Go to S12, S12, S12. Find S12 except K equal 13 and returns a formula on the theorem of Mourad Sultan Ezouidi. Then we obtain the value of S12. Now we see S15, which is okay. So here we say that yes, correct this one. So it will be 3,000 and 3,451. Okay, now it comes here. Now it comes here. So we can see that S6 is going to be different to 0, and S13 is going to be equal to 3,431 times 14 raised to the power 14. Okay, so this is the proof of this new 13-degree from the equation. Okay, is that. Okay, let's complete that. Go like that. Okay, we stop here. We call that, and this is a 0, it's correct, 0. So I'll put go like that. So changing the value of this one. Okay, we stop here. Here, stop. Stop. This is our example. Okay, we told here my professors that the value of S13 is equal to 3000, and is it? Yes, is equal to, this is going to be equal to now. So this one is going to be equal, yes, it's correct, 3431 times 14 raised to the power 14. Here we go step by step. The recursive, this recursive calculation of coefficient ensures that we are working with exact sum rate. Let's go step by step. Here we can see that the value of s minus 1 is going to be equal to amount. This is sk minus 1 formula. Now when and let's say r equals 0 and q equals 0 will obtain n because they have n fruits. And n minus 1 for the 2 is 1 plus 1 combination. N choose minus 1 plus 1 is 0. So n choose 0 is going to be equal to 1. Also the same here, s minus 1 is going to be always 1. And L minus 1 for the 0 will be combination and choose r, means combination and choose r minus 1 plus 1. Okay. Here by convention, s minus 1 equal to 1 and L minus 1 for the 2 equal to 1. By using these components, we calculate the values of sk minus 1 for each degree from 0 to n minus 1, ultimately arriving at the exact sum roots of this formula. Let's now compute and put k equals 0 in this recursive formula or in the theorem of Mourad Sultan Ezouidi, and you will see that the value of s minus 1 is going to be equal to 1. We proceed here, I teach this, to obtain the value of S0, just put k equal 1 in the discrete formula in the theorem of mean, and you obtain that S0 here is going to be unknown, means negative 14 choose 1, which is 14 times 14 is negative 196. This is 196. Okay, 996 plus 14 times 14 is 996. So this one is going to be equal to. So for k equal 2, we find that the value of uh, S1 of 42 is equal to 0. We apply this formula, okay, which is equal to negative combination n choose 2 times L0 squared plus n squared times L1. Okay, now we proceed the calculation. My professors, we want to find S2 also and find S3 also. Okay, so here we go step by step. We go step by step. I'll just come here if possible. I will use like that. It's better. Okay, here we told that this is S1, it's done, it's going to be equal to now. This is how to calculate S1. It will be negative 14 to 2 times 14 squared plus 14 squared times 1. Use your calculator and you figure out that the value of S1 here is going to be equal to now. Meaning this 14 degree from equal. Let's say with 13 degree from equation, we obtain a 14 degree from equation. And we will get a 14 degree from equation, but will be written as quadratic equation, like x raised to the power 14 minus or plus a x raised to the power 7 plus c. Okay, means we collapse this 13, let's say this 14, because we extend 13 degree to 14 degree, and we obtain a quadratic formula. Okay, by setting small x equal capital X raised to the power 7, then we will use the calculate the value of S1 for the 2 dash, and we solve. Then we will, let's say, regroup the roots of these 14 degree from equation in what set of roots. And we'll go back to the recursive formula and we'll give you the exact roots of these 13 degree from equation, because our polynomial is a 13 degree from equation. But here in this example, we extend to say that we can solve the 13-degree polynomial equation by extension. 13 degree itself can be solvable. But here, techniques, strategy, process, okay, pathway that will help you to see beyond 11, 12, 13, 14, 15, 16, 21, 21st, 31st, 41st, and so on. Okay, so here we can see that my professors will calculate the value of as as S2 will obtain that the value of S2 here is going to be equal to another. This is S2. Okay, just calculation. Do your best to calculate. This is the formula that will that derived from the theorem or from the recursive formula of the professor Mourad Sultan Ezouidi, and the professor explains you that here by calculation the S2 is going to be equal to 0 because we make this x14 plus 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 uh, up to the last coefficient has to be like uh, like for the equation. Okay, here the key here is the pathway. Think of, let's say, an nth degree from equation, and how can you solve it by collapsing its coefficient, by excluding all the externals that you want to exclude. This is the power of this theorem. And this theorem is generalized for any integral from equation. And here, as we collapse all the coefficients. Okay, so it's like I don't know. It's like not a game, but it's an approach, stronger approach that will give you exact sample points. This theorem does not approximate. This theorem solves, and gives you symbolic, exact symbol proofs for any integral from equation. Okay, so here we told we continue that when k equals 4, I will obtain S3. Means I'm going to dive into the structure of this semester video or with the theorem or also in the recursive formula that relate Sk with LR minus 1 for the cube, okay, and we will calculate using the formula S3. We give you the first coefficient of this unit for 20 degree from the equation. So here, professor just calculation, the formula is familiarized or just use theorem of Mourad Sultan Ezouidi and then make extension put k to 0, k to 2, whatever. This is regarding to the integrity of the equation. Okay, here we can see here we obtain S3 is here is going to be equal to 0. Now for k equal 5, we obtain by putting k equal 5, we obtain S4 is equal to this formula that has been generalized and written in its lowest term. Okay, and just here, just calculation, you need only the coefficient and 0 up to L4. Okay, because this formula depends only on L0 and L1 and L2 and L3 and L4, and the highest power of this polynomial is 14. Okay, here professor just we calculate this and we figure out the value of S4 here is going to be equal to, and I'll just put these numbers in the calculation and then put the value of S4 here is equal to, I know. So we continue. We want to find S5. To find S5 is easy. Go and dive into the structure of this dive into this structure or substitute k equal 6 in the recursive formula k, and you then after writing the formula in its lowest term S5, okay, just make substitution and say S5 like this, you give it 6 degree from the equation, okay, to this new 14 degree from the equation, and you will just make your own calculation and you will see that here is here is because here is the value of S5 which is going to be the formula. So we continue for cells. We also we want to find a 6 just put k equals 7, and you will see that 6 here is different. And you see 6 is going to be equal negative 3,432 times 14 raised to the power 7. So putting considerations are all experiments equal 0 except 6 and 13 to get second degree equation in terms of x raised to the power 7 all raised to the power 2 minus 6 times x raised to the power 7 plus x 13 equals 0. So we continue. This is just simplification. You can do. This is the formula will give you the value of 7. 7 here is going to be equal to 0. We collapse it all the coefficient of this formula. And now we want to find S8. To find S8, just go to the recursive formula and replace k with 9. We'll obtain the formula that will give you the ninth coefficient of this 14 degree from. Now we just put the integration and we found that the value of S9, S8, so is going to be equal to now. So here again we should complete the value of S9, just put K to 10 in the recursive formula of Mourad Sultan Ezouidi and see how the professor explained it and written, let's say, the, the general formula to find or to give you the coefficient of this new coefficient equation. Here you can see that the value of S9 is just depends on the coefficient and 0 up to L9. Okay, this is the formula. Okay, just substitution. Okay, you get that the value of S9 here is gonna be equal to now, professors, we it remains only 3 steps, 4 steps to conclude. Okay, to write our new 14 degree from equation. Then we will go to solve this new 14 degree, and then after finishing, we'll make alpha equal L0 plus xk. Xk is how the roots are the x roots of this new 14 degree from equation divided by 14. Okay, and then we make a relationship that relates the 14 degree to 13 degree, and concluding after that the exact roots of this 30 degree from the equation. Okay, so here you can see that I will dive into the formula, the recursive formula, and put k equal 11. I will obtain S10. This is the formula that will give you the 11th coefficient. Okay, what's needed here? You need only the highest power n, which is 12, 14, and n0 from here up to n10. Okay, up to n10, we will stop at negative 119,756. Okay, the other coefficient relates to S11 and S12 and S13. Okay, the coefficient. Meaning this formula, this theorem relates the coefficient of the new n degree to the coefficient of the original n degree. This is how it works. This is how can you solve. This is how can you see. You should know how to listen to the coefficient of this new 14 degree from equation, and you should know how to listen to the previous original coefficient of the 14 degree from the equation. This is a big knowledge. Okay, it's a big knowledge to use to extend it, but it's a chance now to at least to think how polynomials work, yes, and behave. Okay, polynomials like let's say the waves of the sea. Okay, you can't deal with if you don't have background. Even ChatGPT or DeepSeek, all of them, although they are considered as AI, artificial intelligence, they can solve this kind of equation, okay, and they allow their their coefficient, coefficient people that they can give this kind of examples, okay. So we continue. This is not our issue, is not our target. The target is to let you learn from you how n degree from equation is now solvable. Okay, and the theorem of Russell really close the door of impossibility. Okay, Abel's impossibility and Galois theory and Newton Raphson and Dan reason. Okay, and a lot of others. lot of mathematicians in the in 200 more, let's say now it's more than 200 centuries. Okay, now we have a new theory, new method, new approach, new calculation, and this calculation does not did not give approximation with exactness. Exact, give you exactness. When you see that, for example, you, you breathe well, meaning that you are in a good health. Okay, and polynomials, in fact, are solvable, not insoluble. Okay, of course, according to Mourad Sultan Ezouidi, that uh, give or gave a contrary example to Abel's theorem and bypass this limitation. Okay, now we solve this is 14th degree from equation point of view, not a second degree, not a third degree, not a fourth, not a fifth, not a sixth, not a seventh. All these polynomials they I worked through, okay, and now we are still we are working on 14th degree. 14th degree means how can you as a human, how can you relate all the 14th degree in one set of rules? Okay, something you may be thinking till now you are thinking that is imaginary. No, not imaginary. This is a reality. This is a fact. This is a theory. This is a pattern. This is an approach. This is a recursive formula that will really relate sk minus 1 to lr minus 1 or sk minus 1 to lk minus 1. Means a polynomial to the power n, okay, has its own coefficient. And another polynomial to the power n has also its own coefficient. But there is a recursive formula that relates this to that, okay, and collapse the symbolic roots and give you the exact roots. Means this is it's called as exactness. It's an exactness, yes. Okay, means we don't approach, we don't approximate roots, we don't give guesswork, sorry, guessed work, or approximation, or estimation. No, we give real, exact, sample roots. Okay? When you tell, for example, one is a root, approximation method will tell you that 0.7234999 is a root. And then he rounds to 1. It's a mistake. It's not true. Okay? Math does not accept, mathematics does don't accept approximation. Okay? Or approach that, let's say, never go back to the earth. Okay? Math, it's mathematics. Math. It's math. Subject, math. 1 plus 1 is 2. Don't tell me 1 plus 52 plus 1 is equal to 3. Rounded. Math 1 plus 1. If you want to run something else. But here we are looking for exact roots, exact sample roots. Okay? So we continue, we told that. Now we obtain a stem that will give you the 11th coefficient. This is the formula that had been derived from the recursive formula or from the theorem of the Prof. Mourad Sultan Ezouidi, and just substitution here, you will find that it's regular S10 is going to be equal to n. Now, my professors, we proceed, we continue. This is k equal 12 has to be put, has to be set, has to be replaced here. So it will be 12 minus 1 will give you S11. That's why it's written S11. K is 11, k is 12 because k is 12, you see? 12 minus 1 is 11, but here is 12. Combination n minus r choose 12 minus r. N raised to the power r between parentheses negative by 0 for 2 raised to the power k minus 1 times lr minus 1 equal to 2. By expanding, by making the binomial extension and making a 0 for the q raised to the power 12 as a common factor, and make the difference between the two first binomial coefficient, means when r equals 0 and when r equals 1, we'll obtain that the formula here started with negative combination 11 choose 1 times combination n choose 12. Okay, L042 raised to the power 12 up to n raised to the power 12 times L1. Meaning in this formula, to find this 12, the 12, the 12th coefficient of this new 14-degree polynomial equation, you need the highest power and you need the first 12th coefficient of the original 14-degree polynomial equation. Each sk minus 1 relates to uh, a k, a k, let's say, a k coefficient of the new nth degree polynomial equation, and here our nth is going to be 14. Okay. Now what's needed here is just calculation. Use your scientific calculator and apply this one. You'll obtain that the value of S11 here is gonna be equal to another. Good job. Good approach. The, let's say, collapse S11 to another. Okay, you collapse it to S11 to get to be a zero. Okay, means that you are like you control the core of n degree from equation, and you extend the impossibility. When n more than or equal to 5, Abel said no. Mourad Sultan Ezouidi opened the door and said, yes, we solved a fifth degree. We also solved a sixth degree. We also solved a seventh degree. We also solved an eighth degree. We also solved ninth degree. We also 10th up to 14th and also 18th and so on. Okay, so this approach can be not can be 100% applied for any from equation. Okay, and now we want to find the 13th coefficient of this 14th degree from the equation. We should set k equal 13 in the recursive formula or in the theorem of Mourad Sultan Ezouidi. So here, professors, just we substitute k equal 13. 13 minus 1 is 12, and here is k, that's why it's equal 13. Here k is equal to 13, and k minus r is equal to 13 minus r. Just calculation and simplifying the binomial coefficient when expanding this sum, okay, and making a 0.42 raised to the power 13 as a common factor and make the difference between the two first binomial coefficient means either this one when r equals 0 and when r equals 1, and the difference of this has to be equal to combination 11 choose 1 times combination n choose 2 times a 0.2 raised to the power 12 up to of course this is 13, 13 this one 13, okay. So then up to N13 and 12. Now I'll just make calculation. I will use my scientific calculator, and I will just need L0 up to we call L12 up to this. Okay, means from L0 up to L12 should substitute it here in this formula to get this 12 coffee, 13 coffee. It's a hard work for you maybe to get this process, this approach. No one of the era of the let's say ancient mathematician think of how think of this kind of recursive formula. But we, Mourad Sultan Ezouidi, we developed it and we discovered and we invented and we formulated and we generalized this to be like you, to be formula, to be theorem in front of you that solves any degree equation. Okay, so here, as we told you, I will use all the coefficients except L13, which is needed for the 14th coefficient of this new 14th degree from the equation. So here you can see that we just make substitution professors and colleagues, numerical teachers, and researchers. We make our substitution, okay, and we found the value of S12 is going to be 0, okay, is going to be equal to another become 0 if it's possible so that we can see it, okay. I don't know where we stop it here. Okay, no problem. So here, professors, It's easy to apply uh, the theorem of the Professor Mourad Sultan Ezouidi and share this formula with your students and share in your area so that will be benefit. Okay, and what's needed now is to find the value of S13. This is 1k equals 14. I will obtain S13. I will just make an expansion of this binomial coefficient and make a 0 for the q raised to the power 13 times a 0 for the q raised to the power 1 will be a 0 for the 14, and this is a 0 for the 14. Put the common factor and make the difference between the first binomial coefficient and the first two binomial coefficients. It means r equals 0 and r equals 1. The difference between that has to be equal to negative combination 13 choose 1 times combination n choose 14. N is 14, so 14 choose 14 is 1. N is 14, 14 minus 2 is 12, 12 choose 12 is 1. Because you can ignore this step, okay? But if you are now working with 15, 16, this formula has to be written as n minus 2, n minus 2, because n depends on the n is the highest count. Okay, if you extend more than n, has to be written and so on. For example, another professor I told I want to find S16. It's a good question. Means this 14 degree from equation you extended to 16 degree from equation. You need S13 and choose 14 never be 1 because it would be 16 choose 14. And here it will be 14 choose 12. And here it will be 13 choose 11. So it's no 1. Okay? But for the last coefficient, for the last coefficient, let's say the n minus 1, the n minus 1 coefficient are an nth degree from the equation, it will be for example uh, it will be minus, this is n minus 1. Okay, it will be minus 1 choose n times okay, n minus 1, it will be okay, it will be minus combination n minus 1 choose what, then n plus 1 minus 1 will be n choose n, so 1 last coefficient is going to be like right. Now just here calculation professors, and you find, and if you want to check your formula is correct, you have to do like that. This is 30. You see the subscript 30 plus n minus 30 is going to be n. N is the highest power, 14, so correct. Okay. So we continue, means that those who are be familiar, those who have been familiar with this formula, they can directly derive this formula without making substitution, without making k equal 3, 2, 4, 9, 100, 200. Means like a system, like an algorithm. Okay, it's an algorithm that works in my mind. That's how it works. Okay, so and maybe I will tell you something, some second key. For example, you see S13 is odd number, has to be negative sign. You see 13, put it here. This is 1. 14 comes from 13 plus 1. According to the difference between that and that, okay? Between the first two binomial coefficient, okay? Now is 14 is, for example, we suppose 13 now is going to be even number, 14 or 20, okay? It will be positive. 20 will be combination 20 choose 1 times combination 20 plus 1 is 21. 21 we here and choose 21. Okay, this is to ignore the confusion, so that we never be confused how to count minus and plus or something like that. Okay, this is depends on your intelligence and how you see formula collapse the coefficient of the original from anything from equation to a new anything from equation, and everything will be formalized and some equation will be reachable. It's something depends big knowledge okay, in the behavior of polynomials and so on. Okay, we continue from that. Okay, here, yes, we will use the theorem. We will use the theorem to figure out the exact roots of the 14 degree equation that has been extended from the 13 degree polynomial equation. So here, Professor, just we make calculation, we'll obtain that the value of, okay, that the value now of S14 is going to be equal to amount. Okay. Here, I will proceed in other words, in other words more. Okay. In other words, why doesn't want this one? Okay. Just give me 1 minute. 1 minute. 1 minute. 1 minute. Sorry. Okay. 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 So just give me 1 minute. Okay, take some coffee. I'll come. I'll come. In other words, we said that sk minus one is going to be equal to a no. Okay. Yes, s0 is going to be equal to 0, s1 is going to be equal to 0, s2, s3, except professors s6 and s13. S6 is going to be equal to negative 3,431 times 14 raised to the power 7. Okay. And S13 is going to be equal to 3,451 times 14 raised to the power 14. So just put the, okay. Mhm. Put x raised to the power 7 equal y or equal factor x and solve for this new second degree from equation x to the power 7 all squared uh, minus 6 times x to the power 7 raised to the power 1 plus 13 equals 0. Okay? And here possible. The Microsoft Microsoft. Okay. Really, I dislike this Microsoft. Okay. Let's see. I will force to work. Okay. Okay. Now come here and hit like that. So here we can just 1 minute. I will share the screen with you. Sorry. Okay. Mm-hmm. Come here as possible. Now we'll solve this together. Okay. This is S5 S13, value of S5. Okay. Mhm. I will share with you just 1 minute. Okay. I'm looking for, yes, this one. So here you can see professors, the value of S13 and S6 are different together. Means we collapse it 13 degree to 14th degree that can be written as second degree from the equation. Here now this is called is 3000, 3,431. Okay. Multiply by 14 raised to the power 14. Here we call that S6 is different to 0 and S13 is different to 0. So here we can see that uh, in like rational traditional method, which often use numerical approximation. The theorem provides precise solution. This ensures that the roots we obtain here are exact and not subject to the errors that arise with numerical method. Once we have a simple coefficient, we use them to find the exact roots of the polynomial. For this equation, we obtain x to the power 14 minus 0 for the x to the power 13 plus s1 for the x12 minus s2 for the x11 up to s13. So we'll keep s6 and s13 and we collapse all the other experiments. Now let's focus on this term involving 6 and 13, which leads us to a simplified form of the equation, meaning that this is minus, you see, minus a 6. A 6 is minus. Minus to minus is positive. That's why here is positive. And this one is plus, so plus what? Plus 3,431 multiply by 14 raised to the power of 14. What's needed now? Just put let the let the x, capital X or small x equal x equal 47 and solve for quadratic equation. Okay. Now I will make this one square. Okay. This one is going to be a negative number because I will make minus a 6. A 6 is negative. You see here, where is it? This one is negative. So plus times this one, I will write it as 3431 times, okay, times this one, okay, times 14 raised to the power 14. And you can calculate this and write it inside. I'll just use the calculation here, calculator. We call that negative 3,431 squared plus 4 times 3431. Okay, this one in fact is equal to 11,758,032. So I'll just put it here. It will be 11,758, 11, 11, 11, 11,758. Okay, 0.057. So 11 million 3,431. Good. So we told 11,756,037. صح؟ Okay. Okay. Let's check here and calculator. 11,758,038. 758,037. Find this. Copy. Put it here on my formula here. Okay. Make Control V. I will try to make it bigger for you so you can see. Not this only, all the others. So here we will solve this particular uniform equation. Okay, so let's go step by step. We call this is 11,758,057. I will put it here. So this is x7 equal. From here we can solve the equation x7 equal as 6 plus negative s1 according to dash multiplied by minus 1 divided. By taking the 7 root of both sides we get the roots. So here what's needed exactly is to replace this one over by 11,758,037. Okay, good enough. This means I will put it here. You see, Microsoft too slow. Too slow. By the way, we are very intelligent by Microsoft. So here we can say that professors that this is the exact sum of roots for this polynomial. The roots are expressive terms in terms of complex exponentials, which is a direct outcome of the recursive steps below. As you can see, Ezouidi theorem does not rely on numerical approximation. The roots we've derived are exact, not subject to the error-prone calculations that come with numerical methods. Here, this approach ensures that we can find the roots exact, even for high-degree polynomials that are too complex for classical methods to handle. For example, here, the approximation method, they told me x equal 1 something and negative something, okay, which is wrong here in this example. But with the Swedish theorem, we have x k equal 14 times negative 3,451 plus root of 11 plus negative, don't forget about plus negative, okay, 11,758 and 37 divide by 2 all raised to the power 7 1 over 7 exponential to k I pi divided by 7. Then the reasoning sign I want to write as, for example, 2k plus 1 and put outside 3k. So here, okay, let's come here first. You see, so this is will helps you. This will help you to solve 14 degree from the equation. The roots are derived. This is the roots are derived. This is for the new 14 degree from the equation. The roots are derived in one cell. In one cell, like you make magnesium. Okay, here you collapse, you regulate all the exact x sample roots of this new 14 degree from the equation in one cell, in one block. Okay, so the roots are derived recursively, where we solve for them step by step. These formulas break down the polynomials into manageable components, allowing us to derive exact sample values instead of approximations. Let's see how this works in practice. Notes here, because of the recursive structure in this video theorem, we were able to derive these roots systematically and precisely without any approximations. So here, this one no need. Let's hit another minimum to the property. Now I will make, let's say, the roots. I will write the exact roots of this possibility. It will be negative, okay, this is a plus, probably 11,758,037 divided by 50. Okay, and then also this one is like that. Okay, plus 1b. These are the exact sample roots of these 14 degree from the equation. Now, if you want to go back to the, we call that is a 14, but we extend it from 50. To solve this 15, that just make alpha k equal L0 plus xk divided by 14 equal L0 plus yk divided by 13, and we relate the 14th to the 13th. Okay, thank you for listening. This is the pioneers Mourad Sultan Ezouidi in life. We call traditional methods which often use numerical approximations. The theorem provides precise sample solution. This ensures that the roots we obtain are exact and not subject to the errors that arise in the method. That now that we have calculated the exact samples, okay, and inshallah, see you next time. Okay, this is the Prof. Mourad Sultan Ezouidi was with you. Okay, I would save this first. Save this. Okay. Thank you for listening and see you next time. Okay. Bye. Thanks. Okay. Sorry.